So yeah, so last class we saw up to capacitance characteristics in depletion region. So we have stopped here. So we saw that in accumulation it is same, just the oxide capacitance. So the charge comes appears on either side of the oxide, very near to the oxide interface. So it is as if just you have an oxide capacitance. That's why it is constant for accumulation region. So in the depletion region, what is happening is the charge separation is increasing with voltage, because one charge plate is at the metal oxide interface, and another charge plate is increasing with XD, and XD increases with voltage. So the charge separation is increasing, so capacitance effectively comes down. Okay, for the same charge, same voltage, if distance is increasing, then capacitance is coming down, right? So capacitance is coming down thus, and it reaches a minimum point at threshold voltage, because that is where XD reaches maximum. We have seen that at threshold, the depletion region reaches maximum depletion width, and beyond threshold voltage, we saw that the depletion width does not increase, because inversion charge will start coming. Okay, so inversion charge starts dominating, so depletion charge will be insignificant. The increase in depletion charge will be insignificant for V beyond VT. So that is what we are going to see now. So what is going to happen for C beyond V equal to VT? So that is today's lecture. So inversion regime of operation, that is V greater than VT. So this is sixth lecture in MOS. So we have three regions of operation, or three regimes. One is accumulation. Only one type of charge is there in accumulation, that is holes accumulating at semiconductor surface. There is only one type of charge, that is positive charge here. It is accumulating. We call it accumulation because hole is majority and holes are accumulating. And there is another regime of operation, that is depletion. Here also there is only one type of charge, that is coming from ionized acceptors because of holes depleting. So holes are leaving from the surface. Okay, so they are getting depleted. They are exposing the ionized acceptors behind, and that is the charge that we see in the depletion regime of operation. In inversion, we have two types of charges. What are those? One is the depletion charge, which is negative, like this, the background acceptor charge, because of depletion of holes. And you see that there is another type of charge, that is inversion charge, very close to the interface. Okay, so these are the two types of charges we have. One is due to depletion, that is acceptors. One is due to electrons, and this is dominant in the inversion regime of operation, the inversion charge. So, but we have discussed earlier that QD saturates at QD inversion. So QD, the depletion charge, saturates at QD inversion beyond threshold, which means it does not increase beyond this value, which is found at the threshold voltage. And that only QI increases for an increase in V beyond VT. So QI only starts increasing rapidly for every increment of V beyond VT. And you know that inversion charge varies with x very rapidly at the surface. So it can be assumed to be like a sheet charge. So this is the picture we have for inversion regime. So here this is metal charge. This is phase charge as a function of x we are plotting. So this is the charge sheet on the metal. And here we have background doping charge, that is acceptor charge, and that is extending from 0 to XD inversion. And we have very near to the surface, we have inversion charge, that is denoted by QI. So that we have shown it like a sheet charge because the electron concentration decays very rapidly, exponentially. So that's why we have denoted it like a sheet charge. Now this is the picture for space charge. Now how does the incremental charge picture look? We see that in the semiconductor, we know that for every increment in voltage, we said that QI only is going to dominate. So the change happens with QI, and QD inversion doesn't change at all beyond threshold voltage. So if QD inversion doesn't change, if QI only is changing, then the change is occurring at the interface, that is oxide semiconductor interface. So the change in charge is entirely coming from change in inversion charge, that is delta Qs change in semiconductor charge is entirely equal to delta Qi change in inversion charge, and minus delta Qs is the corresponding charge on the metal. So you see that both charges are separated by Tox. So as if here also we see only Cox is the capacitance, because we are seeing that the plus minus charge is occurring at the oxide edges. So we have earlier derived the inversion charge to be like this, minus Cox times V minus Vt. We have derived this expression. So from this expression, if you see delta Qs is nothing but delta Qi is what we have understood, and that is equal to minus Cox delta V. Just take derivative. So you will get delta Qi is minus Cox delta V. So delta Q dQs by dV then is the definition of C with a modulus sign. So this is nothing but Cox here, because delta Qs by delta V is nothing but Cox. All right. So that is how you get even for inversion regime of operation. So the curve actually looks like what? So I'm just tracing the curve. So this is V axis, the total capacitance is this. So for accumulation region, that is V less than VFB, you have C equal to Cox. All right. And then in the depletion regime, it is decreasing. We have seen that earlier. And then we say that for V greater than Vt, again it goes to Cox. So both in accumulation, the charge is happening right at the oxide semiconductor interface. The change in charge is showing up at the oxide semiconductor interface. So you will see Cox. And in inversion also, the change in semiconductor charge is happening at the oxide semiconductor interface because of inversion. So here also you see Cox. Only in between, at the surface there is no charge, but it is throughout a depletion. That's why it is decreasing like this. So this is the curve. But the catch here is that, so this is what we expect without going too much into physics. But what is found is this kind of shape you get for C versus V in a MOS cap in measurements only for low frequencies. You are going to get different curves depending on the frequency. That's what was observed experimentally. Then we have to come up with an explanation for why this CV is frequency dependent. All right. So the accumulation capacitance and the depletion capacitance, they don't seem to depend on frequency. But beyond threshold voltage in the inversion regime, the CV characteristics depend on frequency. So what we have discussed so far, which yielded C equal to Cox for inversion regime, is actually for low frequencies. So we have to discuss a bit more physics to understand what is happening at high frequencies. So let us see that. That's what I have written here. So the above discussion holds good only for low frequencies, but doesn't hold good for high frequencies. Now, as a second part in the third regime of operation, that is inversion, which is 3B I'm denoting. And we want to see those characteristics at high frequencies. So now this is the picture we have, MOS, and then there is this M, biased at voltage V greater than Vt, and then you have increased it by delta V. You have added a delta V extra like this. So it is ramping up. So, okay, it can be sinusoidal, but we are increasing delta V. So if and then I see the change in charge across these two levels. Okay, and then accordingly I find the capacitance. So say delta V is increasing like this very rapidly. You can have a sinusoidal with rapid variation, but you can take this also, no issue. So which increases rapidly means what? It has a lot of high frequency components. So high frequency operation. So now origin of the two types of charges. So we have discussed that there are two types of charges, depletion charge and inversion charge in the inversion regime of operation. And we have to see that how they are generated. What is the origin of these charges? That is when we will know what is the change in charge and where does it occur and all that. So origin of the charges is as follows. So depletion charge, it occurs because of movement of holes away from the surface, which occurs due to applied electric field. This movement of holes away can happen very quickly. So what we are trying to say is, yeah, this color is fine. So you have a semiconductor here, and the depletion charge is coming because this semiconductor, and because holes are moving away from this place. So this is oxide. So holes have moved away from the surface when you apply battery here like this. So positive field is like this. So when field is acting like this, for holes also move in the direction of field. So they have moved in the direction of field. So leaving behind ionized acceptors. Okay. So when the moment you apply battery, there will be a field, and due to that field, holes move away, leaving behind ionized acceptors. So this E, instead of extending all over, because we have started creating negative charge because of the movement of holes away from the interface, the electric field starts terminating on the negative charge. So that is how this negative charge is formed. It is movement of holes away from the surface, basically movement of holes in response to electric field. All right. So that is what the origin of depletion charge. Inversion charge, so which is the electron charge at surface. Okay, inversion charge. And we know that minority carriers in a semiconductor arise from thermal generation. So here this is p-type semiconductor, and holes are in majority, so they can easily be provided and easily can be pulled out. Because they are in majority, they can be easily supplied or easily removed. All right. Whereas the minority carriers, they cannot be supplied because this is P. P cannot supply minority carriers from the contact. Okay, from the contact, it is like there is you connect battery, right? So from this battery, electrons cannot be supplied because the P will block. Okay, so those electrons cannot come from terminals like this, because this P will block any incoming electrons. So that can be understood from PN junction. So definitely electrons which are minority carriers in this p-type semiconductor, so they have to be coming from thermal generation. Okay, and this thermal generation is a time consuming process. It depends on temperature and all that factors, right? So thus creation of electrons at surface, which is the inversion charge, takes long time. It takes actually generation time, we call it. So which of this is faster phenomena? Actually, movement of holes away from surface is a faster phenomena, in the sense response of majority carriers to electric field is a very faster phenomena compared to thermal generation of minority carriers. So that is what we have to understand here. So thus, if the delta V increase occurs very rapidly, there will not be sufficient time for thermal generation to supply enough electrons in that short time. Okay, so delta Qi will be approximately 0 if delta V increases rapidly. So earlier what we have seen is, for any increase in voltage, the change in charge is coming from inversion charge, that is increase in electron concentration. But we are saying that electron concentration, increase in electron concentration can happen only from thermal generation, which is a very slow process. So if you increase delta V very rapidly, then thermal generation cannot happen that rapidly and it cannot supply electrons. So what happens now? So without extra charge in semiconductor, we cannot have extra drop of delta V. But you have supplied delta V and electrons cannot come. Then where does this charge in semiconductor come from? So that is the question we should ask. So actually, if you see delta Q as semiconductor charges, sum of inversion charge plus depletion charge. If inversion charge change is 0 because you have changed things very rapidly and electrons cannot be supplied, then delta Qs, the semiconductor charge, has to come from depletion charge. Okay, so considering the same old picture, if this is the picture we have, space charge picture, and if the incremental charge picture at low frequency is this, at low frequency it can be supplied from inversion charge, and incremental charge picture at high frequencies. So at high frequencies, the change in charge comes from this movement of holes away from the depletion edge. So the change in charge occurs at the depletion edge because this is a much faster process. Okay, so as can be seen, you have series combination of COX and CS, as we have seen earlier. Okay, this is not new. So at high frequencies, the movement of holes away happens at depletion edge. So the delta charge comes at the depletion edge, and that is due to movement of holes. So increase in depletion charge. Thus the capacitance seen will be COX, that is this C oxide capacitance in series with CS, which is the semiconductor capacitance. So clearly we have seen it earlier. Therefore, at high frequencies, you have 1 by C equal to 1 by COX plus 1 by CS inversion. Okay, the inversion capacitance at threshold voltage. So 1 by COX plus CS at inversion is XD inversion by epsilon S. All right. So if you simplify, you get the same old C minimum formula. So that is the reason you have high frequency. Whatever C minimum you found, it will saturate. Okay. So at high frequencies. So it is all because this, where does the charge come from? Okay, that is what decides what is the capacitance. And you find that if low frequency is this and high frequency is this, obviously medium frequency would be yielding somewhere something like this. Okay, mix of these two, and that's how it is. And these are very ideal curves that I have drawn, like for example flat here, and then all of a sudden it is not smooth. It is continuous curve, but it is not smooth. It is very flat I have drawn. Then I have drawn something that is coming down. Then very sharply I made it go up and match with COX. So this curve is not smooth, and realistically speaking, curves will be smooth, and this is how they look. So it starts C by COX. If you do, it will be starting at 1, and it will be matching at 1 for very large things, for large voltages, and that too for small frequencies like 10 hertz. Even for 1 kilohertz, if you see, it is becoming flat. Okay, so this is high frequency, this is low frequency, this is medium frequency. Okay, so we will not go into, you can see that what I've drawn here and what I'm showing here as realistic curve, they are similar but very different actually, from in terms of the minimum point here. The C minimum is changing with frequency, and it is not very sharp, it is very gradual. So these things we will not go into details of this basic level course. Okay, so these are the realistic CV characteristics. And if you see what are the range of the C, then you will see that C by COX, where COX is epsilon ox by TOX, it is about 17 nanofarad per centimeter square. So for a TOX of 0.2 micron, but 0.2 micron is very large oxide thickness. So as of now, for latest technologies, you will have less than 10 nanometer oxide thickness. Okay, so it will be 10-20 times smaller than this value. But in general, you can say that it will be in the order of nanofarads. Okay, so that is the order of capacitance that we are talking about. Nanofarad per centimeter square is the order of capacitance we talk about in the MOS capacitor. So with this, we will complete CV characteristics of MOS cap, and let us move to new topic. Okay, so that is something called, okay, before that let me give you motivation. So here, so we have seen that, say, MOSFET is the goal for us because this is the transistor that is mostly used. Simply they call it MOS transistor or MOSFET. Okay, MOSFET they use. quite extensively. So what happens is, how do you get make a transistor out of MOS? All right. So what I have told you earlier is that transistor is like an electronic switch. So you have a load like this. We are not talking about it as an amplifier, but you can it can be used as an amplifier. But let us see it as of now as a switch. So this is the load, and there is a switch, and there is a supply here. Okay, so we supply, and if there is a, if you close the switch, then current will flow through this load because of this supply voltage. And if you open the switch, it will not flow. So through the load, you are allowing the current to flow or not based on a switch. And normally you have this as mechanical switch in your house appliances. You switch on fan, you switch on light, etc. But electronic switch, what is electronic switch? So in the sense, you instead of mechanical force, you apply you apply some electronic signal, and this acts as a closing or switching on, and that is basically coming from a third voltage, right? So for this we have to, and this is the kind of device we are talking about as transistor switch basically, and how we can make a switch out of what we have discussed so far, out of a MOS cap. All right, so let us see how we can make a switch. This circle is what I'm trying to expand. So this is what we have, right? M O S. This M is small, so okay. Now this is P type. Now we have seen that various there are various types of operation. Okay, first you have to bias this, right? Okay, yeah. So now you have to bias this, and you know that the charge inside semiconductor is having three regimes of operation, like accumulation, depletion, and inversion. Accumulation means like this. So sorry, plus charge will come. Okay, this is P type, right? So holes will come like this, and throughout the semiconductor there will be holes, and this thickness of semiconductor substrate is very large. So it is hundreds of microns, and you cannot if you put for example, if you, so this is switch. So what I can say is this I'll ground, okay, and this is that V control or V gate. So I call it VG here, right? So I call it here VG. Okay. So this is the gate controlling voltage. So this is the controlling voltage I take, and this is this side I grounded. Now if VG is less than VFP, we know that accumulation happens, and can we operate it as a switch in that voltage? Okay, so that is one question we have. And VG, changing VG, we have to operate it like a switch, right? So let us see inversion. So this accumulation, inversion is there, and that inversion charge is separated by depletion like this. Okay, so this layer is kind of separate, separate with respect to P type. So there is no connection, and this layer is just at the surface, and you have a background ionized charge. Okay, so if only you contact these two regions, okay, this inversion charge, and if you apply a bias here, they call it drain, say some notation D, then there will be current flow, because I just put a metal contact here, whatever. So I will come to this contact later, but say you have tried to contact the inversion layer, contact the inversion charge or layer, we call it layer, let us say. And then if you apply bias, then this current will, these electrons will flow. these ionized donors, ionized acceptors will not flow, they are immobile. And this biasing is not affecting this P, is not affecting in the sense you have separated this with P by having a large depletion region here. So there is a depletion region. So this VD is not directly talking to this P-type semiconductor. And this is a grounded. All right. So this side it is grounded. Here it is grounded. Here you have applied some voltage. And this voltage is not talking directly to P leading to any current because there is a depletion region here in between this contact and P. So if at all there will be any current, it will be leakage current. So you have an inversion charge here and you just contacted only the inversion charge. And if you apply voltage, this electron will flow. Okay. Now, so now if I change Vg, so this is for Vg greater than Vt. Okay. So, and inversion charge has come. Now, Vg less than Vt. So what happens? Vg less than Vt. So Vg less than Vt, this inversion layer will not be there. Okay. So this inversion layer will not be there. There's only ionized donors, so which are immobile. And this Vd is connected to Vp only by inversion, I mean only by depletion, so which doesn't allow easy charge flow. All right. So it in the sense this Vd and here this contact 0, they're separated, they're isolated without any carriers. So there will not be any current flow because there are no carriers to move. Okay. So this is how you can make it as a switch in the sense Vg minus Vt. So Vg greater than Vt, I will draw. So there is this thing and contact the inversion layer. There will be current vertically due to Vd voltage. Okay. If you contact the inversion layer, there will be current vertically due to Vd voltage. For Vg less than Vt, there is no inversion layer. Okay, so there is no inversion layer, implies current will not flow even if Vd voltage is applied, is on top. So that is how you have a switch. So what is the switch here? We have electronic switch. So this is kind of closing when Vg is greater than Vt, and it is like opening Vg less than Vt. Okay, so Vg greater than Vt, there is I. So Vg less than Vt, I is 0. Okay, I not equal to 0 here, and I equal to 0. So this is the electronic switch we have. Okay, so that is why it is called threshold voltage. The controlling voltage greater than Vt means inversion layer is there, and any bias is there, current will flow. You know, bias on top. This is Vd. So this is Vd. And if Vg is less than Vt, the control voltage is less than threshold voltage. There is no inversion layer, so the current cannot flow because mobile carriers are not there. So even if Vd is there, it is acting like a switch because carriers are not there. It cannot conduct. So I is 0. So this is the picture we have for MOSFET, which is MOS transistor, which is seen as a switch now. As an amplifier, you will see it in next course on analog circuits. So the motivation now is to discuss how this MOS capacitor changes by introducing this contact, because what we have to study is when you put bias, what happens for the inversion charge is what you have to study, because you are biasing, you are applying some inversion charge, to you are contacting the inversion layer, right? So the moment you try to make a contact, that is also acting like a junction. So you have to see the properties of that junction together with the MOS junction to understand MOSFET characteristics. So the next picture is to understand, instead of connecting two contacts both on top and bottom of the inversion layer, what we do is we take only, say, this M, yes, O, yes, and this is M. So this is the structure we have. So we know that inversion layer will come here. Okay. So we have to contact this inversion layer. So what I do is, it is electrons here, because this is p-type semiconductor. Since this is electrons that I have to contact, I will have to make a small portion of silicon here, very close to small portion of silicon. I have to dope it heavily in this corner as N plus. Okay. So here also I will dope it and make the corner N plus. Okay. N plus means large number of electrons, large number of, very large doping. So very large doping means resistance will be low. So this contact portion should not offer any resistance for me. Okay, the screen seen. Okay. So I'm trying to contact. So rather than this, maybe to begin with, I will just put this. So I have to contact this inversion layer. So there is this depletion charge like this. So this inversion layer I can contact, because that is electrons. I contact with N plus. Okay. So here I will contact with N plus. So that only electrons can come and go out of this N plus region. Okay. So this is how I contact a negative charge. So if I want to contact a positive charge like holes, to make contact with holes, I have to put P plus. So in realistic picture, how it is done is, you take a semiconductor substrate, and then that is say P. So what you do is you grow oxide. Okay. And then I'm just giving steps, not in detail. Okay. So what you do is, say you grow oxide, and all that process will be different, but okay, let me not get into the process. So what you will do is, it is planar process, they call it. So they'll make oxide like this. This is oxide, this is metal, this is p-type semiconductor, and here they will convert this region into N plus like this. Okay. So this is how they convert the region to N plus. Now what we have is, you have an N plus region, and if you take this portion, so I have my earlier MOS cap like this. Okay. So this N plus is contacting. So instead what I can say is, so I can take my MOS cap to be like this. So I can just say this is my MOS cap now. Okay, this is what we have analyzed, MOS. So this is what we have analyzed earlier. Now that we have this N plus coming here, okay, so what is going to happen is what we have to see. Okay, I have changed it to flipped horizontal. So because this is how it is done, fabricated. Starting with some semiconductor, you make oxide and you make metal, you make N plus regions, and bottom also you make a contact. So this is how you make a device. So that's why I have flipped it horizontal, but we'll again analyze flipping it vertical like this. So this is where we see MOS. Okay, and then you see that inversion layer here will be contacted by these two N plus regions. So rather than having two N plus regions and then studying how it works, so let us consider only one contact. So what we consider is, for our analysis, just consider this particular one, M O S, and I'll put a N plus region like this, and I'll analyze this first. Okay, so analyze this first, then we'll if you put just one more N plus, it is not going to be difficult to understand, because we have to first understand one more terminal you have put, right? So what happens? Earlier we just have two terminals, one terminal to the left and one terminal to the right. So you have added one more terminal, so it is not going to be easy. We have to understand a three terminal device. Okay, so two terminal device, we have seen PN junction and we have seen Schottky diode, we have seen now MOS capacitor, but now the third thing has come. So for this we have to study little separately. So that is why we study that under the name body effect. Okay, so we study it under the name body effect. So let us start. I'll just take maybe 5-10 minutes. Now M O S, this is P, and here I have N plus. Okay, so now what is of importance is this N plus P, say MOS is ideal, say MOS is ideal. Okay, so implies charge in MOS device should be 0 for 0 applied voltage. Okay, so that's what it is. But now, so this is how it happens, and for that we know that, sorry, here there should be another M. So for that, what we have seen is phi ms is 0 and QF should be 0. So ideal. Now there is this N plus and then P, and N plus will have to be there because you want to contact electrons, and this is N plus P junction. So it is not that you will not have any charge in P type semiconductor now, because this N plus P will have a depletion charge like this. Okay, so this is N plus, so most of the depletion will be in the P side. So there will be small depletion here in the N side. So let us draw it that way. So you have a depletion because of N plus, and there will be small this thing also accumulate. I mean here depletion in N plus also very small. So there is so it is clearly seen that now even in MOS ideal MOS case, okay, so you have some charge in semiconductor because of this N plus contact. Okay, so let us see now what happens when you apply voltage across metal junction. Okay, so this is one particular case, and what we want to study is not when this n plus is 0, but n plus has got some voltage, say, because after all you are making a contact to inversion layer and you are going to bias it so that current will flow across the inversion layer. So you are going to bias it, right? So you are going to bias it. So let us call it VC. Okay, I am biasing it. I am calling it VC. You will understand this notation C little later. Okay, I am denoting it as VC. So here it is 0. Here it is, I am denoting it as VG. Now that we have introduced more terminals, we should introduce subscripts also to differentiate which voltage we are talking about. So the voltage applied to metal, I'll represent it as voltage applied to gate with subscript G, and the voltage applied to this N plus contact, I will represent it as C. Okay, and this side, right side metal, I ground it. So always references with respect to the rightmost grounded terminal to the semiconductor and metal junction. Okay, now the catch is, okay, so now there is VC here. I have applied VC. A MOS is ideal, say. I have applied VC, and there is this N plus P junction. So it gets reverse biased. Okay, because N plus P junction is there, it gets reverse biased. And there is this SM junction, phi ms is 0. So some reverse bias current will flow. So here also there will be some voltage drop, because only then the junction will be allowing current. Okay, so this VC, but since this can actually supply current easily, because this gets like forward biased, this is P and this is like N. So this is P and N. So this is a positive, say VC is greater than 0. Okay, because this is N plus and P, and we want to not have any connection between N plus and P. We want to connect N plus only to inversion layer. So we need to keep it at greater than 0 voltage. Why? Because we want to not have any connection between N plus P. If only VC is less than 0, then this PN junction is forward biased. N side potential is less than P side potential. If this is forward biased, then I will not have current only from inversion layer, but I will also have current from this PN junction, which I don't want. I cannot treat it anymore like a switch. I want to switch off current if inversion layer is not there. Okay, if inversion layer is not there, I don't want to have any current through this N plus region out of N plus contact terminal. So I should not have this PN forward bias. Reverse bias, yes, small leakage current will be there, that I'm fine with it. Okay, I have to live with it. Okay, so that is the reason you will connect always this N plus region to greater than 0 if this is a P-type semiconductor. Okay, so this P-type semiconductor, you connect N plus and make its voltage greater than 0. You cannot have less than 0, because you don't want forward bias current to kill your switch performance. Okay, so this you always forward bias. So this greater than 0. So this is always reverse bias. Sorry. So there will be very small current. So let us say ideal cases 0 current. Okay, so 0 current. So entire voltage drop falls across this reverse bias. If entire voltage drop falls across reverse bias, then we have to see what is happening to the MOS junction. Okay, so you know that if VC is the voltage applied reverse bias, what is the concentration of electrons at this place? So you have a NP junction, or you have a PN junction. Maybe you are familiar with drawing like this. PN junction, you have connected reverse bias voltage, say VC. Okay, and then you draw characteristics. How will you draw? So this is the reverse bias, right? So you have, this is junction region. You have reverse, you have PP naught here, NP naught here. This one is N plus, right? NN naught here. PP naught here. So NN naught, PN naught, PP naught, PN naught, sorry, NP naught. Okay, now reverse bias, how will the carrier concentration look? So this is the edge of depletion. If this is the edge of depletion, I will have carrier concentration coming down like this, and then increasing like this. So here also it's PP naught. What happens is here it comes like this. So it goes to 0 almost, and then it increases like this. You know that this is how you see carrier concentrations in reverse bias PN junction. And what is this concentration? So this concentration is, so from the reverse bias PN junction characteristics, you know that this voltage and this in the depletion region, this is basically depletion region. So from Boltzmann relation, in equilibrium, what will you have? Psi naught is the built-in potential equal to, or V naught, whatever. So psi naught built-in potential is nothing but Vt ln Nn naught by Np naught. So this is psi naught. Okay, in reverse bias, psi naught plus Vc, because that will be the voltage drop across the reverse bias PN junction. That will be equal to Vt ln Nn naught. Okay, that is concentration here by concentration here. So that is N, let us say edge, because that is depletion edge. All right. So that is depletion edge. So then so if you take these two, 1 and 2, and take 2 minus 1, 2 minus 1 gives you Vc equal to Vt ln N edge this minus that, right? So Np naught by N edge. Okay, so 2 minus 1, psi naught is built-in potential, plus Vc gives you this voltage, and then naught by concentration at this point. And if you do 2 minus 1, so N naught, Nn naught, Nn naught will cancel. So N edge will be there. This Np naught will come to the numerator, because minus 1 you are doing, 2 minus 1 you are doing. So implies I will have N edge equal to Np naught e power minus Vc by Vt. So this is the concentration of electrons I have. So in this place, at this place, concentration of electrons is what? N edge equal to Np naught. So okay, this is equal to NH. Let me not write expression there. The concentration there is N edge, and that is in P side at the edge of depletion. So that is why we have derived an expression for it, because that becomes important when you want to derive concentration or the semiconductor charge as a function of gate voltage. Okay, so I'll stop here. I will either record another lecture or take a class, recording in the regular slot tomorrow at 11 a.m. Let me stop here.